Welcome to another deep dive. Today we're going to be exploring the Bloch Sphere.
Oh, this is going to be fun.
It is, right? I mean, it's this tool that we can use to visualize qubits,
Yeah,
the building blocks of quantum computers.
right?
Now, if you think about regular bits, they're just 0 or 1.
Right.
But qubits,
Yeah,
they can be 0, 1, or both at the same time.
it's wild.
It's this concept called superposition, and honestly, it's mind-bending.
Yeah,
But that's where the Bloch sphere comes in.
it really helps us try to wrap our heads around it.
Exactly. So we've got some sources here.
Okay.
And, they talk about how it's connected to things like the unit circle, and even spherical coordinates from math.
Yeah.
What's the basic idea here?
Well, imagine that every possible state that a qubit can be in
Yeah.
is represented by a different point on, like, a globe.
Okay.
That's essentially what the Bloch sphere is.
So like each city on Earth is a different quantum state.
That's a great way to think about it.
Oh.
And just like we use things like latitude and longitude to, locate a city on Earth, we use two angles, theta and phi, to pinpoint a specific qubit state on the Bloch sphere.
Okay, so theta and phi.
Yeah.
That sounds familiar. I feel like that's how we define points on a sphere in math.
You're absolutely right.
Okay.
There's actually a deep connection between the math that we use to describe spheres and how we visualize qubits.
Interesting.
Yeah, each point on the sphere can be represented by those two angles, theta and phi.
Okay, so I'm looking at this formula here.
Okay.
And it says phis qubitin plus I sin phis 2n. Is this how we're translating those angles into the actual qubit state?
Exactly.
Okay, but what is all this? This looks intimidating. What's with that ith in there?
It's not as scary as it looks.
Okay.
Really what it is that the ith part, that bit involves complex numbers,
Okay.
and that helps to describe the phase of the qubit.
The phase.
Yeah.
Okay.
So think about it like this. Imagine you're pointing at a city on a globe.
Okay, got it.
Theta and phi.
Hmm.
Those tell you the location.
Mm-hmm.
But the phase is like an extra spin that you can give to your pointer at that location.
So it's not just where on the sphere, but also how it's oriented at that point.
You got it.
Interesting.
Yeah, and so it's kind of like how you can point at the same spot on the globe, but you could be facing north or you could be facing south.
Okay, that makes sense.
And interestingly, there's this rule in quantum mechanics called the normalization constraint.
Okay.
And that ensures that the probabilities of measuring the qubit in either state 0 or state 1, those will always add up to 1.
So it can't be like 70% 0 and 60% 1.
Exactly.
Okay.
They always have to add up to 100%. And mathematically, this constraint, this normalization constraint, actually leads to the equation of a sphere.
Wait, so you're saying that this sphere isn't just like an arbitrary visual tool.
Yeah.
It comes directly from an actual rule.
Absolutely. That's where the connection between the mathematical representation and this visual sphere comes in. It's not just a pretty picture.
Yeah.
It's a direct consequence of the rules governing these qubits.
Wow. Okay, so we're starting with this basic qubit state, alpha 0 plus beta 1. We apply that normalization rule.
Yep.
And boom, we get the equation for a sphere.
Exactly.
Okay. Then we can use spherical coordinates, our theta and phi, to figure out where we are on the sphere.
Precisely.
Okay. This is starting to click. But one thing that bugs me.
Yeah.
Why do they use half angles?
Oh.
I see theta over 2 and phi over 2.
Yeah.
Why not just the regular angles?
That's a really insightful question. The thing is, if we use the full range of angles, we'd actually end up with multiple points on the sphere representing the same qubit state. And that would be very confusing.
Yeah, that would be a problem.
Right.
Yeah.
So the half angles ensure that each point on the Bloch sphere maps to a single unique qubit state. It's this clever mathematical trick to simplify the representation.
So we're kind of like folding the sphere in on itself.
You got it. Well, almost every point. There is one tiny exception,
Oh, what's that?
the South Pole.
Ah, okay.
And it's actually kind of similar to how the longitude, becomes meaningless at the Earth poles.
Right, yeah.
At the South Pole of the Bloch sphere, the phi angle, it becomes irrelevant.
So we could have multiple qubit states all ending up at the South Pole.
In a way, yes.
Yeah.
But the thing is, remember that phase we talked about?
Okay, yeah. The extra spin.
Yeah, the extra spin. All of those states at the South Pole, even though they might have different phi values, they're actually physically equivalent. They might look different mathematically,
Okay.
but the qubit is essentially in the same state.
Oh, so it's like they're all spinning differently, but they're all pointing at the same place.
That's a great way to visualize it.
Okay.
And it really highlights this beauty of the Bloch sphere.
Mm.
It elegantly handles these little quirks
Mm.
and gives us this consistent visual language to talk about these qubit states.
I love that. Okay, so we have the sphere. Each point is a unique qubit state, except maybe at the south pole, which is fine. The physics works out.
Yeah.
But now I'm curious, how do we actually use this sphere, to understand quantum operations?
Oh, that's where things get really interesting.
Okay.
So imagine taking that globe
Okay.
and physically rotating it.
Okay, so we're physically spinning this sphere around
Yeah,
to see things like flipping a qubit from 0 to 1 or putting it into superposition.
exactly. And each operation, like flipping a qubit from 0 to 1, that corresponds to a specific rotation of the Bloch sphere.
Wow.
And the beauty is all these rotations can be described mathematically using something called polymatrices.
Polymatrices. Okay, those are like X, Y, and Z, right?
Yep. Okay.
Are we talking rotating around the X, Y, and Z axes of our sphere?
You are right on track. Each polymatrix acts as a rotation operator around one of those axes.
Wow.
It's incredibly elegant.
Yeah.
Complex quantum operations become simple rotations on the Bloch sphere.
So any quantum operation we can do to a qubit has a corresponding rotation on the sphere.
Absolutely.
That's really powerful.
It is. And it gets even cooler.
Okay, lay it on me.
There's this fundamental operation in quantum computing called the Hadamard gate,
Okay, yeah.
which creates superpositions.
Right.
On the Bloch sphere, this gate is visualized as a 180-degree rotation around a very specific axis.
Okay.
It's the axis that lies halfway between the X and the Z axis.
Oh, so it's not just rotating around the main axis. We can rotate around A and Y axis on this sphere.
Absolutely. And this seemingly simple rotation is what unlocks the power of superposition.
Wow.
And that's really what lets us tap into the true potential of quantum computing.
I am starting to see why this is so important. This is not just a visual aid.
Right.
It helps us to understand and even design these powerful operations.
It does. And that's not all. There's this other mind-boggling thing about these rotations on the Bloch sphere.
Okay, what is it?
A 360-degree rotation does not actually bring a qubit back to its original state.
Wait, what? Shouldn't a full rotation bring us back to where we started?
You would think, right?
Yeah.
But it's one of the most fascinating and counterintuitive aspects of quantum mechanics. It's this thing called the orientation entanglement relation.
Okay, I need you to break this down for me. How can something need two full rotations to get back to its starting point?
Okay, think of it like this.
Okay.
Imagine you have a coffee mug
Okay, got my coffee mug.
and you rotate it a full 360 degrees.
Full circle.
Looks like it's back to its original orientation, right?
Yeah, it looks exactly the same.
But now imagine that you tie a ribbon to the handle of the mug
Okay.
and you hold the other end of the ribbon fixed. If you rotate that mug 360 degrees, the ribbon becomes twisted.
Okay.
You need to rotate it another 360 degrees, a total of 720 degrees, to untwist the ribbon and truly bring the mug back to its original state.
So it's like there's this hidden twist in the qubit state that we can't see
Yeah,
just by looking at its position on the sphere.
exactly. It's a really profound concept
Yeah.
that highlights this subtle and sometimes really counterintuitive nature of quantum mechanics.
Wow, this is amazing. We've gone from qubits to spheres to complex numbers to coffee mugs and ribbons.
It's all connected.
It is. What else can this Bloch sphere tell us about this quantum world?
Well, that's where we start to venture into a little bit of new territory.
Ooh.
The Bloch sphere, as powerful as it is, does have its limitations.
Okay.
So we can visualize single qubits beautifully.
Mm-hmm.
But what happens when we have multiple qubits that are entangled?
Entangled qubits. Okay, that sounds like we're going even deeper down the rabbit hole.
We are.
But we'll save that for the next part of our deep dive.
Exactly.
Yeah.
The Bloch sphere is just the beginning of our journey into this fascinating world of quantum computing.
Okay, so we've been talking all about this Bloch sphere and how it helps us to visualize single qubits.
Yeah.
But you mentioned it has its limits, especially when we talk about entangled qubits.
Right.
What's the deal with entangled qubits?
Well, that's a great question. It really gets at the heart of what makes quantum mechanics so fascinating and, frankly, a bit mind-boggling. You see, the Bloch sphere is a three-dimensional representation,
Okay.
and it works great for single qubits because their state can be described in a two-dimensional space.
Okay.
So we're basically using the surface of the sphere to map out all the possible combinations of 0 and 1 for that single qubit.
Right, it's like our globe analogy, right?
Exactly.
Each point on the sphere is a combination of those two states.
That's it. But things get a little trickier when we introduce entanglement,
Okay.
because when two qubits are entangled, their fates are intertwined in a way that can't be described by just looking at each qubit individually.
Okay.
Their combined state space becomes much larger.
Okay.
Instead of 2 dimensions, we're now dealing with 4 dimensions for 2 entangled qubits.
4 dimensions.
Yeah.
So it's like trying to fit a 4D object onto our 3D sphere.
Exactly.
No wonder it struggles. How do we even begin to visualize something in 4 dimensions?
It is a challenge.
Yeah.
And it gets even more complex as we add more qubits. 3 entangled qubits would require an 8-dimensional space, and so on.
Wow.
So to truly represent these entangled states, we need to move beyond the limits of our 3-dimensional sphere and use more advanced mathematical tools, things like density matrices and tensor products.
Okay, so our Bloch sphere isn't going to cut it anymore.
I mean, it's a good starting point.
Yeah.
But to really understand entanglement, we need to go a bit deeper.
Does that mean we just give up on visualizing these entangled states?
Not at all. While we may not have a nice, simple visual representation like the Bloch sphere for these entangled states, the concepts we learn from the Bloch sphere, they still apply.
Okay.
So the idea of states, operations, rotations, these are all fundamental to quantum mechanics, even in these higher dimensions.
So it's like the Bloch sphere gave us the foundation, the language, but now we need more advanced tools to kind of explore these more complex parts of this quantum world.
That's a great way to think about it. It's like learning the alphabet before you can write poetry.
Okay, yeah.
The Bloch sphere gives us the basic building blocks, but the real magic happens when we start combining those blocks in really intricate ways.
Okay.
That's where entanglement comes in.
All right, so entangled states may be a bit beyond our visual grasp for now.
Yeah,
But they're still governed by those same principles.
exactly.
Okay, that makes me feel a little better.
Yeah,
Now, there was another concept that you mentioned earlier, mixed states.
right.
How do they fit into all of this? Can the Bloch sphere help us with those?
Ah, yes. Mixed states. This is a very fascinating and important concept.
Okay.
And luckily, the Bloch sphere can still be quite helpful here.
Oh, really? I'm intrigued. Tell me more.
All right, so remember how we talked about pure states being represented by those points on the surface of the Bloch sphere?
Right, so those were states where we knew exactly what the qubit was doing. Like, we knew its position on the sphere.
Precisely. But in real-world quantum systems, things aren't always so clear-cut. There might be some uncertainty in our measurements, or noise in the environment that affects the qubit. And this means we don't have complete knowledge of the qubit's state. That's where mixed states come in.
So are qubits kind of blurry?
Yeah.
Like, we know it's somewhere on the sphere, but we can't pinpoint the exact location?
That's a fantastic analogy. And to represent these mixed states, we move inside the Bloch sphere.
Wait, we're going inside the sphere now? I thought all the action was on the surface.
Well, think of it this way. The surface of the sphere, that represents maximum knowledge. It's a pure state.
Okay.
And as our knowledge about the qubit state decreases, we move inwards towards the center of the sphere.
So the more uncertainty we have, the closer our point is to the center of the sphere.
You got it. And at the very center of this sphere, that represents maximum uncertainty, where all possible qubit states are equally likely. We just have no clue what the qubit is doing.
So the Bloch sphere is not just a map of qubit states, it's also a map of our knowledge about those states.
Exactly.
The surface is perfect knowledge, the center is total confusion, and everything in between is like, well, some level of blurriness.
That's a fantastic way to put it. And this generalization of the Bloch sphere to include these mixed states is incredibly useful in real-world quantum computing.
Okay.
Because noise and uncertainty are unavoidable in any physical system.
Right.
So we need ways to represent and deal with them.
This is amazing. The Bloch sphere, it's like, it just keeps getting more versatile.
It does.
We can use it to visualize pure states, represent operations, and now even handle these mixed states with this uncertainty. It's like the Swiss Army knife of quantum visualization.
It really is. And this is just the tip of the iceberg when it comes to exploring this fascinating world of quantum mechanics.
Okay.
We've talked about single qubits, entangled qubits, and mixed states. But there's so much more out there to discover.
All right, I am ready for the next level of this deep dive.
Great.
What other wonders await us in the quantum realm?
Okay, So we've gone from single qubits on the surface of the Bloch sphere.
Right. To venturing inside for these mixed states.
Yeah.
And even acknowledging that, honestly, the sphere isn't really enough to handle those entangled qubits.
Yeah.
It feels like we're really pushing the boundaries of what we can even visualize here.
It is.
I mean, is there a limit to, like, how much we can even grasp about these quantum concepts?
That's a great question.
Especially when we're dealing with dimensions that are beyond our everyday experience.
Yeah, I mean, that's a question that really gets to the heart of the challenge of trying to understand quantum mechanics.
Right.
You know, we humans, we evolved in this three-dimensional world.
Right.
Our brains are wired to visualize things in 3D.
Yeah.
So when we encounter these concepts like entangled qubits,
Yeah.
which exist in these higher dimensional spaces, it's inherently difficult for us to picture them.
It's like we need to develop new ways of seeing almost a sixth sense for quantum mechanics.
That's a great way to put it.
But okay, if the Bloch sphere,
Yeah.
which is already a pretty abstract representation, starts to break down with entangled qubits,
Yeah.
where do we even go from there? Are there like other tools or visual metaphors that can help us wrap our heads around these higher dimensional states?
Well, it's a frontier of research, really. I mean, some scientists are exploring ways to use different sensory experiences, like sound or touch, to try to represent these quantum phenomena.
Interesting.
Other scientists are developing these new mathematical frameworks
Okay.
that might offer more intuitive ways to visualize these complex systems.
Right.
So it's a really fascinating area of exploration.
Yeah.
And, you know, who knows what breakthroughs we might have in the future.
Imagine if one day we could, like, put on a VR headset and actually experience what it's like to be an entangled qubit.
Yeah.
I feel like that would revolutionize how we learn and teach about quantum mechanics.
That's a fantastic idea.
Right.
It will certainly make these concepts much more accessible.
Yeah.
But even with our current limitations in visualization, it's important to remember that the Bloch sphere is still an incredibly powerful tool. It lays the foundation for understanding those qubits and those quantum operations.
It's given us the language, the basic building blocks.
Yeah.
Now it's about using that knowledge to explore those more complex structures.
Absolutely.
Even if we can't fully visualize them yet.
Right. And it's important to remember that the Bloch sphere isn't just this theoretical tool.
Yeah.
It has practical implications for actually building and understanding real quantum computers.
Right. So all this talk about visualizing these qubits and these operations, it's really leading to building machines that can harness this power to solve real-world problems.
Absolutely. Understanding the Bloch sphere is a stepping stone to really grasping that full potential of quantum computing.
Yeah.
It helps us appreciate that delicate dance of superposition, entanglement, and quantum measurement that makes these machines so powerful.
It's mind-blowing to think about, like, the journey we've taken in just this short, deep dive.
I know, right?
We went from these abstract mathematical concepts to the very real possibility of quantum computers.
Yeah.
Revolutionizing fields like medicine and material science.
Absolutely.
It's amazing.
It's really a testament to the power of human curiosity and ingenuity. You know, we started with this seemingly simple question: how do we visualize a qubit?
Right.
And it's led us to, you know, the forefront of scientific exploration.
This has been an incredible deep dive into the Bloch sphere.
It has.
I feel like I have a whole new appreciation for the beauty and the potential of quantum mechanics.
Me too.
So for our listener out there, as we wrap up this deep dive, what is the one key takeaway that you would like them to hold on to as they continue their own exploration of the quantum world?
I would say embrace the mystery.
Okay.
Don't be afraid to really grapple with these concepts that may challenge your intuition.
Yeah.
The quantum world is full of surprises and wonders.
It is.
And the more we learn, the more we realize how much more there is to discover.
It's true.
The Bloch sphere is just the beginning.
It is.
Yeah.
Well, thank you so much for guiding us through this incredible deep dive.
It's been a pleasure.
Until next time, keep exploring that fascinating world of quantum mechanics.